Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine percentage voltage regulation and efficiency of transmission of a three-phase medium length transmission line using its nominal pi equivalent circuit when values of transmission line parameters and load details are given. A three-phase 50 Hz transmission line of 200 km length has the following constants per conductor per kilometer. Resistance equals to 0.26 ohm, inductive reactance equals to 0.39 ohm, and capacitive susceptance equals to 2.75 micromole. If the power at the receiving end bus is 18 megavolt ampere at 0.8 lagging power factor and at 132 kilovolts, using nominal pi method, we have to compute the sending end voltage, the sending end current and its power factor, the sending end power, the efficiency of transmission, and the percentage voltage regulation. We also have to determine the no-load charging current at the receiving end and the no-load charging current at the sending end. Let us first write down the given data. Load SL equals to 18 megavolt ampere, that is equal to 18 into 10 to the power 6 volt ampere. Line to line receiving end voltage VR line equals to 132 kilovolts, that is equal to 132 into 10 to the power 3 volts. For star connected system, receiving end voltage per phase VR equals to VR line divided by root 3, that is equal to 132 into 10 to the power 3 divided by root 3, that gives us 76,210 volts. Given load power factor cos phi L equals to 0.8 lagging. Let us now determine power factor angle. Phi L equals to cos inverse 0.8, that is equal to 36.8699 degree. Expression for load SL equals to root 3 times VR line into IL. Therefore, load current IL equals to SL divided by root 3 times VR line. Using values we get 18 into 10 to the power 6 divided by root 3 into 132 into 10 to the power 3. That gives us 78.73 ampere. Load current may be written in polar form as IL equals to IL at an angle minus phi L, that is equal to 78.73 ampere at an angle minus 36.8699 degree. This may be written in Cartesian form as 62.984 minus J times 47.298 ampere. Let us now calculate power delivered to the load. PL equals to SL into cos phi L. Using values we get 18 into 0.8, that is equal to 14.4 megawatt. Given length of the transmission line D equals to 200 kilometers. Resistance per kilometer per phase R1 equals to 0.26 ohm. Inductive reactance per kilometer per phase XL1 equals to 0.39 ohm and capacitive susceptance per kilometer per phase BC1 equals to 2.75 micromole. Let us now calculate resistance per phase. R equals to R1 into D. Using values we get 0.26 into 200, that gives us 52 ohm. Inductive reactance per phase, XL equals to XL1 into D. Using values we get 0.39 into 200, that gives us 78 ohm. And capacitive susceptance per phase, BC equals to BC1 into D. Using values we get 2.75 into 200, that gives us 550 micromole, or 5.5 into 10 to the power minus 4 mole. Let us now determine series impedance per phase of the transmission line. Z equals to R plus JXL, that is equal to 52 plus J times 78 ohm. This may be written in polar form as 93.7443 ohm at an angle 56.31 degree. We have obtained series impedance per phase of the transmission line. Z equals to 93.7443 ohm at an angle 56.31 degree, and capacitive susceptance per phase PC equals to 5.5 into 10 to the power minus 4 mho. Let us now determine capacitor charging current at the receiving end. ICR equals to VR into half of J times VC. Taking receiving end voltage per phase as reference, we can write VR equals to 76,210 volts at an angle 0 degree. Using values we get ICR equals to 76,210 at an angle 0 degree into half of 5.5 into 10 to the power minus 4 at an angle 90 degree. That gives us 20.95775 ampere at an angle 90 degree. This may be written in Cartesian form as 0 plus J times 20.95775 ampere. Now we shall determine current flowing through the series impedance. I equals to IL plus ICR. We have computed load current IL equals to 62.984 minus J times 47.298 ampere. Using values we get I equals to 62.984 minus J times 26.34025 ampere. This may be written in polar form as 68.27 ampere at an angle minus 22.695 degree. Now we shall calculate sending end voltage per phase. Vs equals to VR plus I into Z. Using values we get 76,210 at an angle 0 degree plus 68.27 at an angle minus 22.695 degree into 93.7443 at an angle 56.31 degree. That gives us 81,539.705 plus J times 3,543.0589 volt. This may be written in polar form as 81,616.645 volt at an angle 2.488 degree. Now we shall compute capacitor charging current at the sending end. ICS equals to Vs into half of J times Pc. Using values we get 81,616.645 at an angle 2.488 degree into half of 5.5 into 10 to the power minus 4 at an angle 90 degree. That gives us 22.4446 ampere at an angle 92.488 degree. This may be written in Cartesian form as minus 0.9743 plus J times 22.4234 ampere. Now we shall determine sending end current. Is equals to ICS plus I. Using values we get 62.0097 minus J times 3.91685 ampere. This may be written in polar form as 62.1333 ampere at an angle minus 3.6143 degree. We have obtained sending end voltage per phase. Vs equals to Vs at an angle delta equals to 81,616.645 volt at an angle 2.488 degree, and sending end current Is equals to Is at an angle minus phi 1 equals to 62.1333 ampere at an angle minus 3.6143 degree. For star connected system, line to line sending end voltage Vs line equals to root 3 times Vs, that is equal to root 3 into 81,616.645, that is equal to 141.3642 into 10 to the power 3 volts or 141.3642 kilovolt. Phase difference between Vs and Is, phi s equals to delta plus phi 1. Using values we get 2.488 degree plus 3.6143 degree, that is equal to 6.1023 degree. Let us now calculate sending end power factor. Cos phi s equals to cos of 6.1023 degree, that is equal to 0.9943. Lagging. Now we shall compute sending end input power. Ps equals to 3 times Vs into Is cos phi s. Using values we get 3 into 81,616.645 into 62.1333 into 0.9943, which is approximately equal to 15.13 into 10 to the power 6 watts or 15.13 megawatt. Now we shall calculate efficiency of transmission. Eta T equals to PL divided by PS. We have computed power delivered to the load. PL equals to 14.4 megawatt. Therefore, eta T equals to 14.4 divided by 15.13, that is equal to 0.95175 per unit or 95.175%. Now we shall remove the load from the receiving end and calculate capacitor charging current at the receiving end. ICRO equals to Vs divided by Z minus 2 times Jxc. We have determined sending end voltage per phase. Vs equals to 81,616.645 volt at an angle 2.488 degree. Per phase series impedance of the transmission line Z equals to 52 plus J times 78 ohm, and capacitive susceptance per phase Vc equals to 5.5 into 10 to the power minus 4 mho. Let us now calculate capacitive reactance per phase. Xc equals to 1 upon Bc, that is equal to 1 upon 5.5 into 10 to the power minus 4. That gives us 1818.2 ohm. Now we shall compute Z minus 2 times Jxc. Using values we get 52 minus J times 3500, 58.4 ohm. This may be written in polar form as 3500, 58.78 ohm at an angle minus 89.163 degree. Using values we get ICRO equals to 81,616.645 at an angle 2.488 degree divided by 3500, 58.78 at an angle minus 89.163 degree. That gives us 22.934 ampere at an angle 91.651 degree. Now we shall calculate capacitor charging current at the sending end. ICSO equals to Vs into half of J times Vc, that is equal to ICS. We have computed ICS equals to 22.4446 ampere at an angle 92.488 degree. We have determined capacitive reactance per phase Xc equals to 1800, 18.2 ohm and capacitor charging current at the receiving end on no load ICRO equals to 22.934 ampere at an angle 91.651 degree. Now we shall calculate receiving end voltage per phase on no load. VRO equals to ICRO into minus of 2 times Jxc. Using values we get 22.934 at an angle 91.651 degree into 3600, 36.4 at an angle minus 90 degree. That gives us 83,397.2 volt at an angle 1.651 degree. Now we shall determine voltage regulation, that is equal to VRO minus VR divided by VR. We have obtained receiving end voltage per phase on load VR equals to 76,210 volts. Therefore, voltage regulation equals to 83,397.2 minus 76,210 divided by 76,210. That gives us 0.0943 per unit or 9.43%. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learned how to compute voltage regulation and efficiency of transmission of a three-phase medium length transmission line using its nominal pi equivalent circuit when load details and values of transmission line parameters are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.